All right, in this video, we're going to be looking at the relationship between atmospheric pressure and boiling point. A big misconception is students think that the only way to make something boil is to raise its temperature. We're used to this. When we want to cook pasta on the stove, we put it on the stove, we turn it on, and we heat it up. The reason why we have to do this to boil water is because we do not have control over atmospheric pressure. There is another way to make something boil. Boiling occurs when vapor pressure equals atmospheric pressure. Now, normally for something like water, the vapor pressure is far below atmospheric. So you have to add energy, add heat in order to break intermolecular forces, get more gas molecules, raise the vapor pressure until eventually you reach the point where vapor pressure equals atmospheric and you have boiling. That is why we know the normal boiling point of water is 100 degrees Celsius. That is the temperature required to get vapor pressure equal to atmospheric. But what if instead of raising the temperature and therefore raising vapor pressure, what if instead we brought the atmospheric pressure down to the level of the water? So we're going to do something today called cold boiling, or boiling using pressure instead of temperature. So what I have here is a vacuum chamber. This is a bell jar. It's on a rubber mat in order to create a seal, and it is hooked up to a vacuum pump. This is a 2-stage vacuum pump that can get this to almost a perfect vacuum. It's not so good I can do everything, but I can get pretty close to no atmospheric pressure. How does it do this? The vacuum pump is actually removing the natural air gas molecules out of this bell jar and putting them somewhere else, back into our surroundings. So what we're going to do is I have here a normal beaker of water. And I'm going to go ahead and take the temperature of this beaker of water. I have a temperature probe, which I'm going to throw in here. This is a little colder than room temperature, only because I just took it out of the tap. You may not be able to read this, might be backwards on the recording, but the temperature of this water is 23.0, so 23 degrees Celsius. Little colder than room temp, but that's normal coming out of the tap. So this is far below our 100 degrees Celsius. So I'm going to go ahead and put our beaker of water into our bell jar, and I'm going to turn on the vacuum. So we're going to lower the atmospheric pressure rather than raising the vapor pressure. All right, let's go ahead and turn this on. It's going to be pretty loud. I'm starting to see some bubbles forming. Now it's boiling. So you can see those bubbles going up. That is the boiling of that water. I'm going to go ahead and turn off the vacuum. So right now, I've removed all of the air molecules from this, and what happened was the water then was able to produce more of its gas as I removed the air molecules. So as the atmospheric pressure came down to meet vapor pressure and I started boiling, I was replacing that all with water vapor. Now I would not be able to remove that bell jar, right? It is pretty tightly sealed on there because I've created a vacuum inside of it. There's some water vapor, but not enough for me to get that off. So I'm going to have to let the air back in. Now, sometimes this can get a little messy because the force of the air returning might knock over that beaker. We hope not, but don't be alarmed. So what you just heard was all the air returning into that bell jar. So I should be able to take this off now. There we go. So now what I want to do is I want to compare what the temperature of my water is. From traditional boiling on a stove, temperature should have gone up, right? It should be close to 100 degrees Celsius. It's at 22.5 degrees Celsius. The temperature actually went down by boiling this water. Right? This actually makes a lot of sense. The process of boiling, I need to break intermolecular forces. That's what's going to allow me to escape the liquid and become a gas. That is an endothermic process. It takes energy to break those IMFs. So the energy is coming from the kinetic energy of the surrounding water molecules. So overall, the temperature of my water has gone down because that energy has been sucked away to the water molecules that escaped as a gas in the process of boiling. So we can see that atmospheric pressure and boiling point, as atmospheric pressure is coming down, the boiling point is also coming down. I can lower atmospheric pressure to make something boil at a much lower temperature.